and so can I. I think we'll both do it. I hope that won't be. Sure. Record on the cloud. All right. So the first thing is any questions about the lecture. And what I'll do is I'm going to jump to that page. Well, I'm going to actually do homework 22 that I assumed you watched the video by then. I'm going to go through that. And what I asked you was to do some comparisons of, wait a second, now there's some of them not there, but I'll talk about that. Just seeing, I'm going to have to cast this screen. So hold on for 1 second. Okay, can you all see a screen that has fast Fourier transform on top?
Yes, you can see it.
What I'm going to do, I'm just going to add a section here, and then what questions do you have first before we get going? Anybody?
I guess just a follow-up as far as like turn-in homeworks. So we're still on the plan to have 2 a week, you said?
It's right now what I'm going for. There was 1 due today, correct? Right?
Yeah.
Correct.
All right, and I haven't checked my Canvas thing yet, but I assume everybody turned it in, and then I'll have another one up today or tomorrow, sometime between the end of today or tomorrow morning. That will probably be due Friday. Okay. Can you hear me?
Yes, I can hear you.
Okay, and the other thing I want to tell you about is I'm going to go through HonorLock today and get a tutorial and a work through, and we may have just like a try a sample test out with that before we actually go through it once to make sure there's no problems.
Okay.
Everybody's suspicious there's going to be problems with all these new tools that are coming online, so I want to do that before we actually have our test, okay?
Okay.
And now, about any questions you have.
I had one question, and this
Sure.
this might be like, I don't know, but so when we were first going with Fourier transfer, you said that a lot of the transfer could be very like transforms. They could be very similar to Laplace transform.
Yeah. Well, no, well, they are to Laplace, and if you want the DTFT, if you have a Fourier transform pair, where in the frequency domain it just exists between minus pi and plus pi, then you can simply get the DTFT from that. And I can go through one very quickly.
Okay.
It's based on that, but for the Laplace transforms, let me go to a tablet mode and see if I can do this better. I'm going to.
I was just saying that because I was seeing one particular problem that it would have been easier to take a Laplace transformation. I don't remember, to be perfectly honest with you.
Well, Laplace, to me, if you have any functions that have values that are non-zero only for t equals 0 greater than 0, with a couple of exceptions like u of t, then it's much easier to just do the Laplace transform and replace the s with j omega, in my opinion.
Okay.
I mean, if you want a keen example of that, just think about e to the minus at u of t.
Exactly.
Well,
yeah.
That's 1 over s plus a with Laplace. If you want the Fourier for it, just make s j omega.
I think it was one of those, actually. It was like, I don't know. I think it was number 5 on the homework. No. I don't remember.
Which homework?
The homework that was due to today.
This one?
Yeah.
Well,
I think it was, yeah, I think it was one of the last 2. I don't remember which one.
Well, these are pretty straightforward, and I altered this one a little to say about a typical tests question. Somebody asked me about that, and I modified it. But this one is a straightforward one, right? Because this is cosine times e to the minus at times cosine of omega naught t. And we know that goes to what? S plus a over the quantity s plus a squared plus omega naught squared, right?
Yeah.
All right. Well, if you just make s j omega, now you have the Fourier of that.
Yeah.
Another way to get it, is simply take, well, I know 2e to the minus 2t u of t. Can you all see what I'm doing right here? I want to make sure. I'm highlighting. Well, 2e to the minus 2t u of t, the Fourier of that is just what? 2 over 2 plus j omega, correct? That's just e to the minus 2t u of t, correct? And then if it's multiplied by cosine of 10t, that's simply, since some people are going to be missing this, I'm going to go ahead. I'm going to do it below, though. I've learned a lesson about messing with this thing directly. I'll just do this because I want to make sure everybody understands this. If we were given this and we wanted to do it, we could do it this way. We could say that, oops, get rid of that 10, this. So I have this. Well, I know that goes to simply 2 over, and this would be 2 plus j, and I'm just going to use just jw. I'm not even going to make it an omega. You all agree with that? All right, now that if I have that, you can view this as x of t then, or call it x1 of t equal to that. Then if I come over here and I said, well, if I have x1 of t times, sorry, if I have x1 of t times cosine of 10t, right? And that's just going to be the modulation property that you have to know. And that's just 1/2 times the quantity of x of omega plus 10, right? Plus x of omega minus 10. Now I did it this way on purpose. Now what is x of omega plus 10? Well, you take this, and anytime there's omega, you simply make it omega plus 10. So that means this is 1/2 of, let me blow that up a little. 1/2, and then you simply go right here. Make that omega plus 10 plus omega minus 10. That's how you would do it. Follow me, whoever else. That's modulation, and I did it. I can get the first answer right here by remembering the Laplace transform. Correct, class? All right. Let's see one thing here. Trying to see how many people do we have in the meeting right now?
25.
Good, good. That's a fair number. All right, that's sort of a straightforward way of thinking about this. Now, this is just modulation, the standard modulation property. I want to go through a couple of other things. I hope I can do it here efficiently. Now, let me just show you this. Suppose I wanted to know the DTFT, and we've been over this, but I'm going to put it here. So what is DTFT of this, or the inverse DTFT, the I DTFT? So I want the inverse of this. If I have a pulse function of with pi, this would be of omega. Now again, this is a DTFT, right? That's a simple square pulse, and I'll draw it for everybody to make sure I don't lose anybody, but it's simply going to be this. this is basically a pulse. I'm trying to show this at the, oops, omega on that axis, and here, or it's actually capital omega, pardon me. And here, this would have a height of 1, and the width on this, I'm not even going to put it down here, but the width would be pi, correct, class?
Mhm.
All right. Now, that's a standard function. If we allow, but what do we know? If we have this function, if we have p, excuse me, remember this one? If we have p tau of omega, that goes as really tau over 2 pi, right, times the sinc of, and now it's going to be t times tau divided by 2. Do you all remember that? That's the inverse, but I did the two. How many remember that? Just give me that thumbs up sign if you can show me. 1, 2, 3, 4.
Dr. Baginski, was it duality that we used to solve that?
Yeah, yeah. I mean, we got this from duality. Do you remember?
Yeah, I remember that now.
But this is like this is a common transform pair you almost have to know by heart, either from impulse and, a pulse in time and then sinc function in omega, or a pulse in frequency and a sinc function in time, correct?
Mhm.
Now that, you'll notice if tau right here is not greater than 2 pi, and for our case, it was equal to simply pi, right? Right?
Mhm.
Now you can change that to capital omega, and then simply replace t over here by n. So now I have, this is omega is the DTFT. That's a simple ideal bandpass filter, low pass to be specific. Do you agree with that, everyone? Can you all see what? Right?
Dr. Baginski.
Go ahead.
So because the DTFT is done between minus pi and pi is why that you can change the small omega to the large omega, right?
That's right. For this thing to work, the actual Fourier transform has to be non-zero only between minus pi and pi. If it is non-zero outside of there, then this won't work. All right?
All right, thank you.
Sure, but you all see this. Now, this is still a function that is non-causal, but it is nevertheless the response to this. And here's what gets interesting. I'm going to get into this today, but we're going to make what's called a finite impulse response filter. We can actually use this and shift it over to the center of the data we collect. If we have a total number of n pulses, if we make this shift from not having an argument n here, but n minus capital N over 2, then we can use this and convolve it with the input signal, and it will be as if an ideal filter worked on it. I mean, it's close to it, an approximation. I'll get to that later. But what I want to do now is this. I mean, are there any other questions about the homework? If you can unmute, if you have one, unmute your mic or type out the message and somebody alert me to it. I'm going to go ahead and continue with what I planned for today. Usually I give about 20 to 30 minutes for questions and answers in a lot of these things, because I give you a lot of homework that's, I figure you're going to have questions about. So now I'm going to go to the PowerPoint of the DTFT, and this is something, can you all see it? All right, this is straightforward. We've been through this. This is just the development of the DTFT, and it goes through some examples. It shows you some things about rectangular and polar forms. This is non-essential. It does the transform of a pulse that has a 1 value from minus q to plus q. This is a very common transform that you have to know. So this is the standard pulse we were looking at, right, just now? With me? And you get this, right? And that is that's very similar to a sinc function, because if the arguments of omega right there are small, if you just take a look at this, then the argument of sine of omega over 2 is about omega over 2 for small values of omega. All right. Then this is just the plot. So if you have 0.5 to the n u of n, you know the transform of that is either this or that. And I show you the plot of the magnitude and the phase, and we've done that. Then this is something that's a little different. Here I have minus 0.5 to the n. That's a high frequency signal because the value of minus 0.5 to the n is decaying, but it's decaying in a way that's like a sine. It's being multiplied by a decaying sign. Think about it. If n is odd, that's a negative value. If n is even, it's a positive value. So it's jumping up and down, but it's decaying. Can you all understand that? All right, and it shows the spectrum. And as expected, the spectrum right here will have a lot of high frequency signals. If you use the inverse the FFT shift, you'll see this. And I talked about the FFT shift, didn't I, in here? Class? No? Do you remember FFT?
I think you briefly touched on it.
All right, I'll go through that today. Anyway, for the inverse DTFT, you can get it directly by doing this integration. And let me mention something here. Really, if you want x of n, what my recommendation is, do it this way. And I'm going to put it over here. I hope you can see what I'm typing. What you're going to do is have an integral. Lower limit, I always put at minus pi. And then the upper limit at pi. My internet connection is unstable. That's interesting. Then you put x of capital omega here. If you want to do it by integration, usually you don't even have to because you'll know by duality how to get this. All right. And or you'll know the transform pairs times e to the j capital omega n, or really n goes in front usually. And then it's, come on. I don't know why that thing's not putting the superscript there. And then it's d omega. So now that's how you would get x of n. I wouldn't go from 0 to 2 pi, but you'd simply take the function x of omega and integrate it from minus pi to pi. And this is the definition of the inverse DTFT. Usually we just use pairs. We know the pairings, okay, the common ones. So you won't have to do that. If you look in your table, they'll have them. All right, now this is where we're going to go. The DFT. Do you remember me talking about this at all? The discrete Fourier transform?
A little bit, not a ton.
All right, not a lot. What I want to do is try to do this on this tablet and write better than usual, if you don't mind. So let me try to do this. So now I've got to cast this screen. Give me 1 second. I can't see it, but can you see the DTFT 4.2 right here? Everyone?
Yes, I can see it, and I can see you writing too. So
Okay, I'm going to go ahead and just go from the definition of the DTFT. So this is x of omega. I hope you can see that. Is equal to, and here it's equal to a summation from n equals minus infinity to infinity of x, this is the definition of e to the minus j n capital omega. That's just the definition, right?
Mhm.
Now, here's what we do. We're going to say, we're going to have, this is going to make it real, something we can actually process. And this is what happens with radar. We turn our radar on when we're listening, and we collect a certain length of data, a data stream. We're going to sample that data, quantize it, and store it. But they're going to have n points. So we're going to collect n samples. Does that make sense to everybody? And n will always be, it'll be 2 to the n. It's always going to be some, it'll be 2 to some power n, but it'll be a large number. So now what I do is this. I start here, then I modify, and I say now I'm going to take samples from n equals 0 to really n minus 1, because there's going to be n samples. If 0 is the point that I start, if that's my data set, and with MATLAB, it won't be a 0, it'll be a 1, but it's the very first data point that I collect. I sample and I store it. And I'm giving I'm saying the indice is 0 here. It'll be consistent with the book. So now I have x of n, but now I don't use this. And I'll tell you why. I know that the frequency range will be 2 pi. It'll go from minus pi to plus pi in the actual omega domain. Do you agree with me? And I don't have a continuous frequency because I don't have an infinite series in the time domain. So now I do this. I put exp, as I've done before, and it's going to be minus j. And then what we do is we take 2 pi and divide it by n. Now what that is you've taken 2 pi, the total frequency spectrum available to us, and you divided it up by n. So there are delta of omega pieces, you might say. Do you follow me? And then you multiply this by both n and by k. Now, let me get to this. What this really is before I had omega n up here, and that's equal to, it's still going to be equal to 2 pi over n times nk. And all I've done is look at the exponent right here for the exponential, the exponent on that e, and then look at this. You'll notice I've equated them. Everybody see that? I went through this once before. Everybody? Can y'all see what I've written here? If you can't, give me a thumbs up so I make sure I know I can see. I can only see 3 faces besides that.
What is the K for again? Is that just a constant?
No, it's going to be an index in omega. This is going to be, and I'll get to this right now. Now, whoever asked that's a great question. Get rid of that n. It appears on both sides. And now you can say that really what I have here would be omega sub k. So what I'm saying here, and this is important, now these are the discrete frequency points. No longer do we have an infinite number of points, a continuum from minus pi to pi, but we have discrete values. The smallest sample would be 2 pi over n. That's the delta of omega. Can everybody see that?
Yes.
All right. Well, I heard you. All right, good. Keep that in mind. And this now will not be called x of omega sub k. It'll just be x of k. And this is the DFT. It's the discrete Fourier transform. Okay. It's just x of, I never knew how bad my handwriting was until now. Okay. Y'all with me? All right.
Mm-hmm.
What I also want to say is what we will use in MATLAB is the FFT, and that is the fast Fourier transform. And I'm going to speak on that in a second. Does everybody follow me? So that's the DFT. And you can do this manually for a few things. Suppose I just have this. Didn't I do this problem for you where I gave an example of this being applied before? I seem to recall that. Yes? Anybody remember? Let's do it. We'll take this as an example. So here's my example of actually doing a DTFT, or I'm sorry, a DFT. I'm just going to say X is equal to 1, 0, 1, 0, okay? This is in the n domain, and I'm going to put an underscore there, and that means n equals 0. Do you remember that? Whenever the underscore appeared, that's where n was 0.
Yes.
Now, with that, let's do the DFT of this. So the first thing I have to do is this. I have to say, well, X capital, why does that go? Capital X of 0. Now that would be, remember, it would be a summation from n equals 0 to, there's 4 of them, 4 minus 1 would be 3, right? Of this value, it's really going to be of x of n times e xp to the minus j 2 pi over n, which is 4, right? Times n times k. That's the definition. Does everybody agree with that?
Never mind. Sorry.
Does everybody agree with that, class?
You
Give me a
repeat
thumbs up.
that exponent again?
This is e to the minus j 2 pi over n. For this one, n is equal to 4. That's the data length right here, right? There are four elements there, correct? You all see it? All right. I can simplify this and make that just pi over 2, can't I? Right there. I'm gonna.
What is the other n in the exponent?
This here, x, this, you mean? That's the argument, I mean, it's the indice on x. The n here is the summation. It goes from 0 to 3. See it? Who asked that?
Me, Jacob.
All right, Jacob, it goes from 0 to 3. So this n here, right here, would go from 0 to 3 as you index on this n as well. But if this is 0, k equals 0, what happens when this is 0, k equals 0? Class?
Exponent goes to 1.
E to the 0 is 1, so you get rid of it. So just get rid of that whole, get rid of that whole thing. And look, now you got this, right? Well, that's just what? You're summing the values from 0 all the way up to 3. And what's that value, class? 1 plus 0 plus 1 is 2, isn't it? You agree with me?
Yep.
All right. What is x? Do this yourself. What is x of 1? It's the summation from n equals 0 to 3 of x of n times e to the minus j, and it's pi over 2. I've taken care of the 2 pi over n is pi over 2 to the nk. Well, here, k is 1, so it's just in there, right? Because remember, this indice here is k, correct, everyone?
Can you explain one more time what k is?
Okay.
K is the index on the frequency. This is a DFT. It's likened to the DTFT or the Fourier transform. So this is in the, you could think of it as in the omega sub k domain, where k is going to be an index on the increment, delta omega. With me? If you're not, hang in there and you'll see it in a second. Now, what's this value? Go ahead and work it out, you guys. Here, this is in classwork. Go ahead. You're at home, you got computers, you got paper, pencil. Just do this mathematically, take care of it. Well, what happens? I've got the first data point is 1, right? That's at n equals 0. So it's 1 times e to the 0 is 1, isn't it, class?
Yeah.
All right, the second one is 0. Well, 0 times anything is 0. So don't worry about that. The third one is 1, right? And it would be times 1. And what happens here? Well, this is n equals 0, 1, 2. That's 2. So this would be times e to the minus j pi. Do you all agree with that?
Yes.
Yes.
All right. What is e to the minus j pi? Same thing as e to the j pi. What is that? It's minus 1, isn't it? Just take one at an angle of 180 degrees. It's -1, isn't it, class? So what is this going to be? 1 minus 1 is 0, correct?
Mm-hmm.
All right. Finally, what's the last one?
That one's 0 again.
Do you all see it? All right, now I'm going to try to do this. I'm going to go to MATLAB. Actually, for n equal 1,
I have a question, Dr. Baginski.
shoot, pardon me. Go ahead.
So I understand in the x of 0 in the first one that k was equal to 0 and just wiped out e basically, and in the x of 1, k is just equal to 1. Have we gotten to x2 yet?
We're going to do it right here, and we made a mistake. This is where k equals 2. All right. Can you see what I'm writing?
Yeah. So there shouldn't there be a
2
2 at the end?
That's
Okay,
right.
that was my question. Yeah.
You're right. So they would cancel. And then because n is 2, it would be 2 pi. So this is really e to the minus j 2 pi, or 1 plus 1, and that would be 2. That was my mistake. Do you see that?
Okay.
I did not see what just happened.
All right.
I'm
Let's do
confused
this.
as well.
X of 2. All right. That's k equal 2. All right. Now, what is that mathematically? It's still the sum of x of n times
Okay,
e.
I have a quick question.
Go
So when we did the first one, when n was equal to 0, was k equal to 1?
Yeah.
Right. Wait a second. Yeah. But it doesn't matter. 0 times anything is going to make it 0.
Okay, yeah, okay. I thought you said because k was equal to 0 that the exponent was 0. So that's where I
the
got
first
confused.
one. That's the first one. Right here. When I put a 1 in here, well, let me just write this, then we'll talk about it. When I put this is nk, just watch this. Now this is, if k was 0, then there would be a 0 here would make that 1. And then it would just be a sum of the values of x from 0 to 3. Now, if k is 2, then this would become a summation from n equals 0 to 3 of x of n, right? E to the minus j. Now it's 2 pi over 4, so it's pi over 2, but k is 2, so it would really be j minus j pi times n. And that would be equal to, the first value at n equals 0 is 1 times e to the 0, plus, and there would be e to the minus j 2 pi, because n would be 2, correct? Remember our value. This is 0, 1, 2, 3. So the 1 appears when n equals 2 and makes that 2 pi. And what's that going to be? 1 plus e to the minus j 2 pi. Isn't that the same thing as e to the j pi, 2 pi, plus j 2 pi? Remember, every 2 pi, what happens? You go back to the same point. So it's really 1, so that's 2. Isn't it, class?
Mm-hmm.
If you understand that, please show me with a thumbs up so I can see who does and who doesn't. I've got, okay, looks like most of you do. Now, I want to show you with MATLAB how you can do it. So
Well, I do
Dr.
have a
Baginski?
question. So that would make the very first one we did, was that incorrect as well?
no. The very first one was what? X of 0, right?
Okay, yeah, you're right. Sorry.
Okay. Now let me show you.
What was the issue with k being equal to 1? I'm not sure I follow with that.
It's not an issue with k. It was k equal 2 was a problem.
But you marked out 1 and put 2.
Forgot to put the 2 in the exponential. This is actually sub k, right? Not 1. Is that what you're talking about? That's
yes,
k,
but is
the index.
is
This
there,
is k equal 2, right?
But why could k not be 1? Is there a reason that we can't have it equal to 1?
I think it's because in your original x equals, your
Mhm.
second value is a 0.
No, but if it
so
is,
you ignore
if it
that.
is 1, what happens? Just do the fundamental. That's the definition, right? Anybody
Mhm.
else? All right.
Yes.
If you talk about the value when k is 1, right? When
Mhm.
k is 1, I get rid of this. Then I still have to do the sum from n equals 0 to 3, right?
Yes.
Mhm.
All right. Keep going. That would be the first value. N is 0, so it would be 1. Oh, boy. Now I don't know what happened there.
I think you just have to scroll down.
Is it on this one? I
I
don't think it
think
is.
Isn't it?
No, it's not on this one. It's here. All right, bear with me on this. Here's what I was talking about. This right here is going to have k equal 1, right? Right here. Y'all see it?
Yes.
That's k equal 1. All right, take the first value, 1 times 0, times e to the 0 is 1. So that's 1, right? The second value is 0. 0 times anything is 0. Third value is 1, right? Sorry. Third value is 1, right? So I put a 1 here, then it's e to the minus j 2 pi over 4, or really pi over 2 times 1, right?
Yes.
So it's going to be 1 plus e to the minus j. And take a look at that. This is going to be pi there, correct?
Yeah.
Mhm.
And that is minus 1.
Yes.
All right, so that goes to 0. But here's what I wanted to show you, if I can. I want to show you in MATLAB, if I can get this to the screen. There we go. I hope you can all see that. Now in MATLAB, here's how you can do this. Called the FFT. The difference is for this one, it has to, here's my vector, right? Here's my points, x equals 1, 0, 1, 0. And for an FFT to work, there are always 2 to the n points. Now this is really 2 to the 2 points. But if you don't have 2 to the n points, what will be done is they'll add zeros to the end of your thing until you do have 2 to the n. It's called zero padding that we'll talk about later and the effects of zero padding. Generally speaking, if you have an option, always collect 2 to the n points where n's an integer. For instance, 256, 512, 1024, right? 2048 and so forth. Now, when I look at this, if I want the actual FFT, which is the same thing as the DFT, identical. Watch what happens. What did we get? We got 2020, didn't we? Now, if you wanted to get, if that was the DFT and you wanted to get the original waveform X, what you could do is say this. You could do IFFT. All right. I hope you can see that, of my answer. And now I'll get back the original signal. Can you all see that?
Yes.
Let me give you a more difficult or a different type of example of this. Here, what I'm going to do is say that, let me clear all, and then close all. Now, I'm going to create X, and I'm just going to say it's, maybe, let me go XX equal 1s, and I want 1, comma, I want 100 ones. And then after that, I'm going to say X is equal to, this is called collation. I'm going to put XX, that's 100 ones, comma, and I'm going to add to that, just a space there, zeros. And I'm going to have 1 by, and here it's going to be 1024 minus 100. So now the total data length will be 2 to the n, an integer value. and put a semicolon there. Now what I'm going to do is see what this looks like, and I'm just going to plot X. So I want to see, make sure I have a pulse waveform. That's what I'm going for. With me?
Mhm.
Actually, popped up in a different window. So that's what it looks like. That's what I'm going for. It's a pulse, but notice the length. It goes out to 1,200 points, roughly. And not quite out there, but it's out there. But that's a simple pulse, and it starts at 0, right?
Mhm.
Yes.
Now, watch this. So if I have that, if I want the DFT of that, let me put clear all. Or no, I better not put clear all. Now I'm going to put capital X, all right? What now? Matter of fact, let me do this. I want to spend a little time on MATLAB showing you stuff, so I'm going to bring this to a different scene. Can you all see a MATLAB window,
No.
class?
Oh.
Now we can.
Now
Yeah.
we
Yeah.
can see it. Yeah.
You can?
I think you're having
Yes.
lag issues.
Yeah, that's normal. The network's probably having trouble. And I'm going to go ahead and, I said this the other day, but I'm going to pay for high-speed internet. I mean, the highest speed. I thought I had the high speed, but apparently 100 megabits download and whatever, 11 or 12 upload isn't the fastest. I guess 300 is available. All right, now I'm going to just see what this looks like. Plot of ABS, that's absolute value of X. Now, watch this carefully. Now, can you all see this?
Yes.
Mm-hmm.
One thing you'll notice is that there's a whole lot of frequencies down here. You notice how there's a 0 here.
Mhm.
I said the DTFT repeats itself from -pi to pi and from pi to 3 pi and so forth. This is a shot that is equivalent from 0 to 2 pi. Now, MATLAB does something for us that's nice. I'm going to show you this in parts, but are you with me right now with what I've done?
Yes.
I can do this, and I can go ahead and say, I'll call it X or capital XS, that's shifted. And if you type FFT shift of X, right? Now, this is a neat feature that MATLAB has. And then, come on. I'm sorry, I did that. And then if I type plot ABS of XS, I want you to see this. I hope it comes up. Oh, can you all see that?
Yeah.
Mhm.
All right, it basically took the two pieces and it took the one from the left, one from the right, and put them on, like put either side of the 0, but it shifted it out here. And now if I do this and I plot it versus, let's see here. What I'm actually going to do is just show you it here. I have this done already. This is basically what I've done so far, only I have 64 instead of 100. And then I have NW as the length, and this is my function that I've been dealing with. And then I get the length of that data stream. The total number of points is N, that's here. I create an integer I, and then after that, I say that's the sampling rate, TS, and I let X be equal to FFT of X, and then XS is the FFT shift of that. Now, here's something interesting. I didn't get to this yet. What this is saying that the equivalent frequency in the omega domain would be 2 pi over N, Now that's 2 pi over n is the delta of capital omega. Now, when you divide it by TS, now it becomes the small omega equivalent, and I is simply an indice. Now, you'll see what I'm doing in a second. This would be in radians, by the way, and I'll let you see that code. This, I know you got to go in a second, but bear with me. This is in hertz right here. Don't worry about that. But I think that's right. I'm not absolutely certain. So if I take a look at this and run it, no doubt I get an error.
You added too many in the front, too many parentheses in the front.
No, it'd have to be the same in the back though, right?
It highlights which one is the same.
Let me see if this works. Oh, it's right here. Forgot this. Right there, right? And then I got too many back here. Let's see if that works. I had another plot below it, so I just want that stuff. There we go. Now, here's what I was getting at. This is, we did a sample data series. This is the actual frequency here. Where is that plot? What this is a plot, but it's in frequency in hertz. And let me show you what I mean right here. If I take a look at this, this frequency on the x-axis is in hertz. I've shifted it so I centered it at 0. Now, I don't have time today, but I was going to show you that the actual first lobe here corresponds exactly to the 0 in the sinc function. Remember, when you have sinc of omega tau over 2, when omega tau over 2 is equal to pi, it's 0. Do you remember that?
Mm-hmm.
Mm-hmm.
The exact zeros and everything are now there. So if we do an FFT, then an FFT shift, and then we shift the center frequency. So we take half of all frequencies, omega sub i's, and just take those things and divide them, would be omega I of n divided by 2, and subtract that from the indice omega I, you'll get this plot. I know I've said a lot there, but what I'm trying to tell you is now we've got something that is identical to an actual Fourier transform of a non-sampled pulse series. So we can think in terms of the Fourier transform and the properties. You all see this here?
Yeah.
And unfortunately, I didn't get to windowing. Ruth, you have to go, right?
Yes.
All right. What I'm going to do is give you some exercises using the FFT here and the inverse FFT so that you'll get familiar with these operations in MATLAB. I'll ask you to do them for next time, but they'll be due. The formal homework will be due on Friday, okay? And today I have to get used to this honor lock. Has anybody here used honor lock?
Yes.
How did it work?
I don't know how it works for the teachers, but for the students, they have you scan your room with your webcam, and you can't have like any other screens visible or anything. You can't open other tabs. And your face has to be visible at all times. There's a lot of rules with it.
Was it a multiple choice test, or was it a written test where you had to take a picture and turn it in?
It's multiple choice. I don't know how you'll be able to do it with a written test.
No, you can do it. You take a picture. Everybody's got a camera phone. You take a picture of it, and then you send it to your email. And then from your email, you'll put it into Canvas. Or you probably can get to Canvas directly from your phone if you take a picture.
But you couldn't pull up your email while on honor law.
Yeah, it doesn't let you open other tabs, I don't think.
Plus, like having your phone out would be like against the.
All right. Well, how do you? I mean, you've got to have a way to submit assignments, right? If you're given a test, you're telling me the only thing I can test is going to be multiple choice.
I think so. If you're using that system,
Then
that's
I'm
the
not
only
going
way
to use
that
it.
I've seen it.
I'm going to get a tutorial on this, but if that's the case, then we're not going to use that. That's for the birds. But I'm going to find out today how to do it. Let me tell you one thing about this too. What we're going for is this real life processing. You all see how basically this looks like a Fourier transform. That signal was a pulse right there. And it literally is. If I actually do one thing here, if I simply say that x limit would be equal to say minus 10, 10, and I do that. If you want to run something, you highlight and hit F9, and then I look at this function. Well, I actually didn't shift it to the absolute 0, but you can see, say minus 30. I'll shift it to the actual 0 in a second. You can see what I'm doing is this is the first. No, I need more points too. It's got to be. How many points did I have here? 256. Make it 1024. This will be a little clearer. All right. Y'all see how basically you can see from here to here, that's the first lobe. Well, this point would correspond to a frequency where the argument of tau omega over 2 was equal to pi. Or I'm sorry, is equal to, yeah, pi. And I'll show that to you next time because I'm running out of time. You're gone, aren't you, Ruth?
Almost.
All right, you can go. I'll give you some homework, and I'm going to stick around. You have questions, some of you guys? Does anybody have any questions? Because I've got an office hour coming up from 11 to 12.
I've still got a question.
Okay, go ahead.
Well, I mean, I'm still stuck on the K's and stuff.
All right, let me go back to the other screen. Hold on. Okay.
You're going to post the video for this as well, Lydia?
Yeah, it's probably all going to be on the YouTube channel.
Okay.
If you can put it on YouTube, fantastic. The further away you can get from this university system, the better you are, in my opinion, because there's so many things that might go wrong. All right. So are you looking back on the original screen with the written one right here?
Yes.
All right. Now, what's your problem, or what's your question, I should say?
Okay. So when we find capital X sub 0, that is when K is equal to 1, correct?
No, that's K is equal to 0. X sub 0 is this, the indice here is 0.
Okay. So K goes from 0 to 3, like.
No, N goes. The DTFT form, the DFT definition is this: X of K is equal to the summation of N equals from 0 to N minus 1. N, capital N, is the number of points. So if you go from 0 to N minus 1, you've covered every point of X of N. That's going to be the data value at N times E to the minus J. And then there's 2 pi divided by N. That's the data length. That's how many total samples you take. Then it's multiplied by N. times k. Now n will be summed out, just like you integrate t out of a Fourier transform when you do e to the minus j, e to the minus j omega t dt times your x of t. Here you sum out n. Now x of 0 right there is nothing more than a sum of just x of n from n equals 0 to n minus 1. It's just the summation of all the x values.
Okay.
Are you with me?
Yes.
And remember the similarities. The Fourier transform to the DTFT. Same basic thing, only the DTFT sampled the signal, right? It's sampled at a certain rate, TS, that doesn't appear in the DTFT. Now when we have a DFT, we truncate the length of that sample. Now this is manageable. We can do this in real-time processing. And we can literally collect the data for maybe a millisecond, 2 milliseconds with radar. And then we can immediately digitally process that and get a DFT of that. And we can adjust it with an FFT shift. And then we can shift out the frequency and we can see the signature of the actual, what's out there in the frequency domain. Can you appreciate that?
Yeah.
This is real processing now. We're getting down to something that is applicable. All right. Now, I can ask you this, just do this long-handed with me. Do you guys need like a couple minutes of break before we go on?
Well, I mean, that was just my question. I think I'm.
All right, how about other questions? A lot of people jumped out.
I have a small question. Is it okay if we could walk through some of the MATLAB code, like fairly slowly, just to make sure that we got everything?
Why don't we create a MATLAB code from scratch?
Okay, that would be perfect. That would be very nice.
All right, what I'm going to do is this. First, I got to take the camera view. You all seeing a MATLAB thing here? What I'll do is this. I'll add another one. This is the way I do MATLAB. When I start, very first thing I do in a code, I do an M file always. So this is called the command window. Like if you put dir, it'd show you what's in your directories. If you type, you know, I think you know most of the stuff. You can find all your previous commands. This is the command window. I rarely use that to write any code. You go up here in what's called, and you also see it says editors, stuff there. Now here I've got untitled 3. So the way I always do a MATLAB code is start by clear all, close all, and then CLC. That gives me a clean screen. You don't have to do this, but and there's probably one command that does all 3, but I'm used to doing it this way. After that, I type down anything I'm going to use over and over again that are constants. For instance, if, I don't know, if A is 10, I'll put it there, and if B is 100, I'll put it there, and anything else, say just omega naught was equal to 2 times pi times, say, f naught, and then I'll make f naught back here equal to 100, something like that. And every time you put a semicolon, what it does is basically prevent the thing from reappearing in the window after you run the thing. If you don't know what I mean, let me show you. If I can. Wait a second. I'm trying not to just put that on there. All right. Don't worry about that. That's what we have so far. Now, after that, when you're going, let's see, which question did you have?
I was just wondering if you could just do like an example problem.
How about we do the one we just did? 1, 0, 1, 0, right?
Right.
Put a semicolon so it doesn't appear. Now I'll put x, capital X, equal FFT of x. That's the fast Fourier transform of that.
Okay.
Now after that, the only thing I'm going to do, I use what's called a stem plot, STEM, of x. And what that does is show you actual magnitude values of x in the actual, with a little circle on top. And I'll show you that right now. Let me just run that. And we'll just call that DFT 1. Y'all see how that's a circle there at 2, and that's the DFT is actually what I've shown. And what I can do is this. I can put 1, let's see, 1, hold on. I'll just do this. If I do this one, that's a stem plot of just the original one. And then this one will be a stem plot, should be a stem plot of the second one. There's not a lot of information there, but let's do something, make it a little more interesting where you can see it. Suppose now I do this. I'll make this x equal to, it's going to be two things. Ones from 1 to, make it 100, and then zeros of 1 comma, and this is going to be 1024 minus 100. The reason I'm doing that is I want the total number of points there to be 2 to the n points. And then after that, I'm just going to plot that. So plot, see what it looks like. And it'll be x. And I'll just do this part right here. So this is going to be a pulse. What did it say? Oh, this is supposed to be a semicolon. Wait a second. What happened to my code? Did it all disintegrate?
It disappeared.
There it is. Let's try it again. Let me just comment that stuff. If you actually hit Control R, you can comment stuff out. And if you want it back, if you highlight it and then hit Control T, I believe it takes it back. Those are just handy things to know. What did I do now?
Should it be a comma in the ones array instead of a colon?
Yeah. Yes, it should be.
And that means that it's a 1 by 100 array. Is that correct?
That's right. And this is what it actually looks like in terms of an envelope. It's just a pulse.
Right.
It starts at 0. So if I have that, and then I do the first the FFT of that, and then I'm going to do a stem on that, but I want to stem not the x, but the absolute value. of x. It's going to look weird, but it'll be at the extremes. You see how right around 0 and right around, this is equivalent to 2 pi, you've got the major data, right?
Right.
Mm-hmm.
Now here's what it'll look like if I'm going to modify it. First, I'm going to say xs is equal to FFT shift of x. And then after that, I'm not even going to use a stem. We'll just take a look at what this looks like. Plot ABS of XS. This should push everything right to a single point where we see it's clear. Everything's centered about that point. Follow me?
Mm-hmm.
But that isn't the right, it should be at 0 frequencies. And this is because I didn't do that. I didn't subtract off this center frequency. So then if I do, I'll call it X, just X2, and that, no, better yet, let me do it this way. I'll actually get the frequency. So the actual frequency in the omega domain, let's do it this way. I need to get I'll call capital N is equal to the length of X. Now that just tells me how many points there are in that vector X that I created that's a pulse. After that, I'm going to create a variable I and let it be equal from 1 to N. And then what I'll do for my frequencies, I'll say omega sub I. You realize what I'm doing here is just finding a length, and I know that same data length that I have in N will be the same amount of points I have in the omega domain. So here, I could put sub k if you want to be consistent with my notes and make that omega sub k. And that would be equal to, first you start with 2 times pi, because that's the data extent. Then you divide it by N. That's how you chop it up. That's delta of omega. Now it's going to be times k. K is an index that goes from 1 to N. Are you with me so far?
Okay, so 2 pi over N is like your bounds, and you're dividing it by the number of data points that you're sampling, I guess? The number of data points you have?
Just about exact. It's 2 pi is the total spread in frequency I have available to me. It repeats outside that range. So when I take 2 pi by N, that tells me the actual frequency step I can see when I do these, when I increment k. When I multiply it by k now, that value is, think of it omega sub naught, omega sub 1, omega sub 2, where omega naught would be the fundamental. Our fundamental here would be 2 pi over N.
Okay, that makes sense.
All right, now remember this is still capital omega. If you want it in the actual frequency domain, what I have to do is this. I have to divide this thing by N times TS. We might as well put a TS in here just so you get an appreciation for it. TS would be the sampling rate, or this time between samples. Make it 10 to the minus third. That's 1 millisecond. And this really, the way you do it in MATLAB is just 1 e to the minus 3.
Could you say that again? Sorry.
Say what?
With the N over TS. I mean,
when I have, if I don't have TS here, if I just have that?
Yes.
Then what I actually have is capital omega. All right, that would be, that's just, the maximum it can have, the maximum value would be 2 pi. The minimum value would be 0.
Okay.
And what you can actually do if you want to, I'm going to leave it like that for now. You can be clever and you can actually say, you could let k start at a negative value. I'm going to just leave it like this. It would get too fancy. I don't know why that thing's got that there.
Because there isn't a parentheses around 2 pi.
Yeah, that's right. There we go. Now what I'll do is this. Remember that goes, this particular one goes from 0 to 2 pi. I don't want that. I want to go from minus pi to 2 pi, right?
Right.
So now what I do here is I take that, omega sub k, and then I subtract off omega, pardon me, of n over 2. And I think I have to do n over 2 plus 1. Is it n over 2? I think it's plus 1, but let me just leave it at that for now. Try this just for a second. Yeah. Now, that's still in the omega domain. You'll notice it goes from minus pi to pi. Can you all see that?
Mm-hmm.
Yeah.
How many do we have? Just 4 on here? How many are left? How many people can you see?
I think it's just us 3.
Okay, that's all right. That's all right. That's still all right. Now, the next
another
one.
quick question, sorry. But why did you add 2 plus 1?
No, it's n over 2 plus 1.
Okay.
See, n over 2 is half the data stream. The plus 1 is because, remember, you actually started 0.
Okay.
And I'm going to, what I'm going to do is show you this. Now, what I want to do is take a look closely about the origin. So I put x limit, and then I'm going to go from, say, minus 10 to 10, or not minus 10, minus 0.1 to 0.1. And run it again. I think y'all can see that, right?
Mm-hmm.
Now, the first zeros here, this is the first 0. I hope you can see where the cursor is. That occurs when the argument, if you think about this pulse function right here, it's got a width of 100 points, right? It goes from 1 to 100, I mean from, 1 to 100. And there's a total number of points at 1024. Does that make sense?
Yes.
Yes.
All right, so that's like tau would be equal to 100 times TS in the real world. And if you think about this, p tau of t goes to tau times the sinc of omega t over 2, right?
Yes.
All right, I want to show you something. Oh boy. Let me do this. Let me stop right there. And what I'm actually going to do now, this omega, that small w where you see the cursor, that is really capital of omega. Are you with me?
Yeah.
The minute I
Yes.
divide that by TS, now I have actually omega. So if I have it multiplied by TS right there, it's really dividing by NTS, isn't it, class?
Yes.
Now what I have is the actual frequency in omega. And then what I'm going to do is one more thing. Then I'm going to say f of k, right, is just going to be equal to omega sub k divided by quantity. Actually, why don't I just do this? I'll just do this, make this f, and get rid of the 2 pi. And so we will be in hertz. Can you all see what I've done? Instead of having omega being in radians per second, now that's f in hertz, or cycles per second.
Oh, okay.
And then I'll put f right there, and f right there. And now I'm going to plot the actual transform of this thing. And we're going to do a comparison real quick. See what it looks like. And I thought so because I got to change this. Let me just say for a second. So that would be I got to check one thing on a pad and paper. I have all right. My omega is 2 pi over n ts times k, and that's 2 pi f. So get rid of that. So that's tau times the sinc of 2 pi f tau over 2. 2's go. So it's pi f tau. So pi f tau has to be equal to pi, or f is 1 over tau. That's exactly it. So let me point you, do something for you here. I'm going to go from over 100. First, I'm going to do this. I'm going to show you something. I don't know why this thing's blinking so much. Oh, now I do. If you look at this, I'm going to first get rid of TS. Are you with me?
Okay.
Now, what I've done here is I've gotten rid of the sampling rate that would put it in terms of hertz. This is going to be something that it won't be periodic in 2 pi. It'll be periodic in 1.
Right.
All right. Now, let's see what this looks like. Matter of fact, I'm going to not even put any data limit or any limits on the x-axis. I want to just take a look at this. And that's what I'm looking at. Most of the information is right around 0, right?
Right.
All right. Now, after that, what I'm going to tell you is that 1 over tau will be, well, let me get that back up here for a second. Where's my plot? Oh, got to run it. If you look at this, you can't see it, but the actual value of tau is 100 points, isn't it? It's on for 100 points, and then it's 0, right? It's 1 for 100 points. So 1 over tau would be 0.001, correct?
Mm-hmm.
Take a look what the first 0 is. It's at 1 over tau, and I'll work this for you. Now I'll put this axis limits, and it's going to be at point. This is going to be 0.01.01. Just about nailed it.
Mm. Okay.
Let me go from 0.011. Well, it should be 0 right at 0.1, and I don't have enough data points. But if I went and I took a look at this, where's my thing? Instead of making that 1024, make that 2048. Let's see if that does it.
2048 or?
That's better. See, I didn't change the actual number. See, the tau stayed the same. It was 100, 100, but I've increased the length of the duration, right?
Mm-hmm.
2048. So let's see if that does it. Still creeping down. It's just about to 0. It's trying to get there. And if you increase the number of data points, you'll see, in fact, that this point here compares to 1 over tau, where tau would be the data length.
Okay.
Do you understand that, Nick?
Yes, I'm with you.
All right. Now, I don't know, you're going to get some of this for homework, but here's the cool thing about this. If we go ahead, I didn't have time for this today, but if we wanted to see what it would be in the real frequency, if we were sampling at TS, then if we simply multiply by TS here, or capital TS, and I'm assuming I'm sampling 1 millisecond, every millisecond, then what I can do here, get rid of that limb, multiply this by 10 to the third, so it would be 11, and this would be plus 11, that would be minus 11. Make it minus 12 so we get a little more breadth to it. And this is 12 hertz. So we take a look at this. And you see, if we go from minus 12 hertz to 12 hertz, we get this. And if we let it go, instead of 12, make it say 48. So it'd have a spread of 96. Now what you're going to see is it looks just like a sync waveform. Exactly. See that?
Neat.
Now here's the thing.
So all you've done there is that you've sort of changed the you're just scaling the axis. Is that correct?
I'm just changing, yeah, the window
Okay.
where we're looking. But you'll see this is an exact sync function. Now here's another thing that's interesting. See this height right here?
Mm-hmm.
The value is 100. The true value of this when we do normalization would be 1. Now technically it's not. Remember, it's tau times the sync function. So if tau is 100 points, it's this high, right?
Yes.
All right. Normally what we do when we plot this, because we used FFT shift and stuff like this, you would multiply this by TS right here. I don't have time today, but we literally get a value of 1. And this signal that you see right here, that is literally a very close approximation to a continuous time signal that would have the same proportion of on time to total time. In other words, same duty cycle. And it's done in discrete time. And we use not a DTFT, but a DFT. Follow me on that?
Yes.
I think so.
Well, the DFT is what I told you today. I showed you today.
Mm-hmm.
And you're going to have some homework on that. But I'll tell you one thing you're going to see. This second peak right here,
Mm-hmm.
that is 13.56 dB below this point. And there's a way we can get it a whole lot less with windowing, and that's coming up. Now, did you guys have any more questions about any of the homework so far?
I'm pretty good personally, but
I think so as well. Yeah.
All right, I'm just going to pull up, hold on. So I'll ask you guys this. You're a pretty good indicator of what the class is doing. This we haven't got to. This is going to be windowing, and that's next lecture.
oh boy.
Windowing is very powerful. We're going to do that. But this is DFT, and this is going through the nuts and bolts of how it's computed. It's not important right now for you to know that in detail, but the DFT is a very efficient, the FFT is a very efficient way of doing a DFT, and that's the reason you need 2 to the n points. This PowerPoint of the DTFT, did anybody have any questions about this? It's more or less just a show and tell of what we've done.
I haven't had time to look over it thoroughly personally, but
Okay.
Yeah, it's the same here.
And I guess you didn't do this then.
I did actually watch the lecture, and that it's just I didn't particularly look at the PowerPoint.
All right. And you took care of homework 1, right?
Mm-hmm.
Yes, sir.
All right. Well, I'll see you Wednesday. I'll put some more stuff up there, and I've got to go through this honor lock. And if I don't like honor lock, I won't use honor lock. I'll figure out something else.
There is a good chance. I know that honor lock, as other people were saying, I've never personally used it, but a lot of people are saying, you can't have other screens and things of that nature. I don't even know if you'd be able to have the book, and you had said that you would wanted the test to be harder questions, but open note and book. So
if I can eliminate the book, even though part of me's thinking that's not going to happen. I mean, if I can eliminate certain things, I'll give you tables myself.
Sure.
And I normally never give tables. I never give anything. But if I give you tables, the problems go up in order of magnitude and difficulty.
Mm-hmm.
And that means the grades get even more skewed usually. But let me see about this stuff, and then we'll I'll get back to you on this. But did you understand today's lecture, even though it was a little slow?
I think so. I don't quite see the, like, I understand, you know, the math that we're doing. I see the definition and I know what we're doing with the math, but I don't know particularly why we would do something like this.
DFT?
Mm-hmm.
Why would you do a Fourier transform?
I guess to get it in a simplified form. So you
Why would you just do a continuous time Fourier transform of anything? What does it tell you?
We want to look at the frequency domain and where the energy of the signal is.
Sure. And what do you do when you design a filter? Don't you look at its frequency domain spectrum? Low pass, high pass, band pass, right?
Mm-hmm.
And when you have that information, that rolls right over to a DTFT filter, right? If it's between minus pi and plus pi.
I'm still not quite seeing the jump there, sorry.
If you had a filter that you designed, a low pass filter that was from, say, it had a low pass band of 100 hertz, right? Let's say it was a pulse. So that would be an omega of 2 pi times 100. I mean a tau, pardon me. The tau right there would be 2 pi times 100. That would be the width in the omega domain, correct?
Yes.
All right, now if you went to the frequency domain, all right, to the capital omega domain, remember capital omega is small omega times TS.
Yes.
TS is the samplings. So that means the upper frequency of interest. Boy. Let me write this down. If I had P and I wanted it of 2 pi times 100, that means the frequency there, the omega I'm talking about, which would be tau, would be equal to 2 pi times 100. And that would be equal to that omega times TS would be capital omega. So if I had 2 pi times 100, and then I sampled that thing at a rate greater than at least 100 hertz or 200 hertz. Here, let me just write this down for you because it'd be easier for me to do it this way. I'm going to go down here and just say, look, suppose I want P of tau of t, and I know that goes to right?
Yes.
All right, now we use duality, and that means tau, oh, sorry, tau divided by 2 pi times the sinc of t times tau,
Right.
divided by 2, right, is equal to, or transforms, sorry, to 2, I've got rid of the 2 pi already, just P tau of minus omega, but really it's just plus omega because of symmetry, correct?
Mm-hmm.
All right, now go into the capital omega domain. Let me take this and you'll see the steps. Now, if this is capital omega, right, this becomes n, right?
Yes.
And there's a stipulation between these two things right here. There was one thing that happened. Now I assume TS was equal to something.
Right.
Okay.
And that means capital omega was equal to small omega times T sub S. Got me?
Mm-hmm.
All right. Now, that's omega domain, right?
Yes.
So if I wanted a 100 hertz low pass filter, a low pass filter that cut off everything above 100 hertz. My tau here would be 100, correct?
Yes.
Right? What does that make omega? Well, that means the omega, or the width in the omega domain, well, that's 100 hertz. Sorry, it's 100 times 2 pi, my bad. Are you with me? Because that's omega, correct?
Yes.
So if it's 100 hertz, it would be 2 pi times 100, or 6.28. There's 628 basically radians per second. Now over here, if I say TS, and here's the thing, if this is 100 hertz, right, this has to be at least 1 over 100 hertz, preferably faster than that. It has to be 1 over the highest frequency, twice the highest frequency of interest. So that means the sampling interval would be equal to 1 over 100 times 2. I'll just put it there, 2 times, or 2, how about I do it this way, times, come on, 100. That's sampling at 200 hertz, or once every 1 over 200 seconds. Are you with me?
Mm-hmm.
That means this omega, right, would be 1 over 200 times 100 over 2 pi, or it would be pi. See that?
Right.
I mean, this would be, sorry, would require, I said that wrong. What that would be is this. That means that where'd my cursor go? What that means is tau, for the one I showed you there, would be equal to the omega times TS. So it's really going to be 100 times 2 times pi divided by 200. Or it would be just what? Pi, correct?
Pi. Mm-hmm.
That means this would be pi, right? And then that means this would be just 1/2, right?
Right.
And that means this is going to be pi.
Okay.
And that would be, this would be the impulse response right here. You see that?
Yes, I think so.
Yeah, that's h of n, right? That's h of omega, that's h of n.
Mm-hmm.
That makes sense.
Remind me to show this next time too, because they need to see the relationship.
Right.
Good with that?
Think so, yeah.
All right. All right, let me get some homework up there and find out about honor lock and see what other university businesses occurred. I can only imagine it's getting interesting.
All right, well, thank you, Dr. Baginski.
All right, man.
You.
All right.
Take care.
You too.
All right, bye-bye.